Let us understand the continuity equation. So herein I have drawn a pipe through which fluid is flowing. Let us say the fluid is flowing as shown over here. So we understand that some amount of fluid that has entered the pipe at this end, this amount of this amount of fluid will be exiting the pipe from the right end. So let us say we are analyzing this amount of fluid per unit time. Alright. So let us say this length happens to be dx1. This much length happens to be dx1. And this length happens to be dx2. The area of cross section at this end happens to be A1. The area of cross section at this end happens to be A2. Alright. So what can we write about the mass of the fluid that is entering? So let us say the mass of the fluid that is entering is dm1 and the density at this point happens to be ρ1. So the density over here is ρ1. Similarly, the mass that is exiting is dm2 and the density at this point is ρ2. So what can we write per unit time? The incoming mass dm1 by dt. So the rate at which mass is incoming into this pipe has to be the same as the rate at which mass is leaving the pipe, because there is no storage of mass. Basically there is no deposition of mass anywhere inside, so the incoming mass has to go outside as well. Now we understand that mass is nothing but density into volume, so we'll have here ρ1 into d volume 1 by dt is the same as ρ2 into d volume 2 by dt. This we understand. Okay. So now what is volume 1? Volume 1 over here is nothing but area 1 into dx1. This is nothing but volume 1. Similarly, here volume 2 is going to be equal to area 2 into dx2. So here I can write ρ1 a1 dx1 by dt. This is going to be equal to ρ2 a2 dx2 by dt. Now consider what is happening. dx1 by dt is nothing but the velocity of incoming mass dm1. So this is nothing but v1, and dx2 by dt is nothing but the velocity of the outgoing mass. This is nothing but v2. So what can we thenceforth write? We can write ρ1 a1 v1 to be equal to ρ2 a2 v2. This is what we can write. In most cases, we are dealing with incompressible fluids. So whenever we are dealing with such incompressible fluids, what we can write down is ρ1 is equal to ρ2, let's say a constant density ρ, because the fluid is not going to be compressed. And hence we get the standard continuity equation A1V1 is equal to A2V2. Now if we were to analyze exactly what is the meaning of A1V1, then we understand that A dx is nothing but the volume dV. So this is nothing but d volume. I am avoiding writing d capital V because in order to not confuse with the velocity. So I am writing d volume by dt is nothing but area into dx by dt, because d volume is nothing but area into dx. This we understand. So this is nothing but AV. So when we say that A1V1 is equal to A2V2, what are we essentially saying? We are essentially saying that the incoming rate of flow of volume, let us say the volume that is coming in from here is the same as the outgoing rate of flow of volume. That is what we are claiming basically, which is exactly correct. And if the mass was to be considered and if the density were variable, then what were we claiming? We were claiming that the incoming rate of flow of mass is the same as outgoing rate of flow of mass, which is also exactly correct. So the incoming mass is going to be the outgoing mass per unit time. Okay, so this is the continuity equation in its standard form for incompressible fluids. For a compressible fluid, you may have to use the density variable form, which is like this form basically. For incompressible fluids, you can directly use this form. Alright, so let me box this very important equation, which we will be using many a times. So this is our continuity equation. Alright. Now, if you have been given a situation that is something like this, then from here, let us say the volume flow rate is A1 V1 from over here. Alright, so let us say from here the volume flow rate is A2 V2. Then the volume flow rate of the output is going to be equal to A3 V3, which is going to be the sum of A1 V1 plus A2 V2. So let us say this is A1 V1 over here, this is A2 V2 over here, then the output A3 V3 is going to be nothing but the summation of A1 V1 and A2 V2. So what I can write down over here is A3 V3, the volume emergence rate is going to be equal to A1 V1 plus A2 V2. So what is this equation saying or stating? This equation is essentially stating whatever is the incoming rate of flow of volume from these two parts or portions of the pipe, this incoming rate of flow of volume goes here in the output, and this incoming rate of flow of volume also goes here in the output basically. That is what is being stated. So this is the continuity equation, and this equation is very commonly used while studying fluid flow.